Hello, in this section we will discuss an essential chemical concept, the mole. Given the infinitesimal nature of molecules, chemists became aware of the impracticality of using molecules as a measure of larger observable substance quantities. As a result, a new unit was invented, the mole. A mole is technically defined as the amount of substance of a system which contains as many elementary entities as there are atoms in 12 grams of carbon 12 by UPAC, the most important chemistry federation. In other words, a mole is the number of particles present in 12 grams of carbon, where each particle has a mass of 12 Dalton. It is not coincidental that the value for the mass of a single molecule of carbon in Dalton equal that of a mole in grams. The choice of carbon to define a mole was arbitrary. There is, in fact, a fixed number, a constant, such that when multiplied by the mass in grams of a single molecule with x as its mass in Dalton, results in a sample of mass x grams for any kind of molecule. That fixed constant is the amount of molecules in 1 mole, 6.02 times 10 to the 23rd power. Then, if we measure that amount of molecules of, for example, oxygen 16, we would find that our sample weighs exactly 16 grams. The mole is a universal constant, essential to measure greater amounts of substances. Now we will discuss Avogadro's number, the constant we just described. Its value is approximately 6.02 times 10 to the 23rd power. This value allows us to do different calculations in order to find conversions or equivalent quantities between atoms, molecules, and grams, by noting that a mole of atoms equals Avogadro's number worth of atoms, which also equals the molecular mass of the given substance, except the unit is switched to grams.
Hi guys, I'm Liv, and today I'm going to be talking about molar mass. Just to review what you learned in an earlier lesson, the term mole refers to a specific quantity of atoms, 6.02 times 10 to the 23rd atoms. We will use this quantity to find molar mass, which is simply the mass of 1 mole of a substance. The molar mass of any element is equivalent to the atomic mass of that element. So when you look at a square on the periodic table and you see the atomic mass listed, you will also know the molar mass of that element. We use oxygen as an example, and you'll see that oxygen has an average mass of 15.999 atomic mass units. Therefore, the molar mass is 15.999 grams per mole. Another way to say this is that 6.02 times 10 to the 23rd oxygen atoms have a mass of 15.99 grams. Now we can use what we just learned to find the molar mass for a single atom of a different element. Here I have an example for an atom of nitrogen. The periodic table says that the average atomic mass of nitrogen is 14.01 atomic mass units. Therefore, the molar mass of nitrogen is 14.01 grams per mole. When it comes to finding the molar mass of a molecule rather than just a single atom, we can use the technique that we just learned. If the molecule is made up of one element, then we multiply the molar mass of a single atom of that element by the number of atoms in the molecule. So the molar mass of N2, or diatomic nitrogen, would be 28.02 grams per mole, because we multiply 14.01, which is the molar mass of a single atom, by 2, which is the number of atoms in the molecule, and we get 28.02 grams per mole as a result. If the molecule which we are trying to calculate molar mass for is made up of more than one element, then we do calculations for each of the element's molar masses independently and then add the results to find our answer. If we use this skill to find the molar mass of water, then we will have to find the molar mass of 2 hydrogen atoms and the molar mass of a single oxygen atom. The molar mass of hydrogen is 1.008 grams per mole. Therefore, two atoms would be 2.016 grams per mole. The molar mass of oxygen is 15.99 grams per mole. So 2.016 plus 15.999 gives us 18.015 grams per mole as the molar mass of a water molecule. Because we know the components that make up the water molecule, we are able to determine the mass percentages of different elements with some simple division. Because H2O is made up of two different elements, we will do two calculations. We divide the mass of two hydrogen atoms from the total mass, then multiply it by 100 to make it a percentage, and round to 2 decimal places. We will do the same thing for oxygen, dividing the mass of one oxygen atom by the total mass and multiplying it by 100 to make it a percentage, and then round to 2 decimal places. These calculations tell us that hydrogen atoms account for 11.19% of water molecules' mass, and oxygen atoms account for the other 88.81% of the water molecule's mass. Previously, we had been working to find the molar mass when given a certain number of atoms, but now we are going to practice finding the number of atoms when given the molar mass. I made up an example here for us to practice. We're going to look at a molecule of lithium, which we are told has a molar mass of 34.705 grams per mole. The periodic table tells us that a single atom of lithium has a molar mass of 6.941 grams per mole. So we can use this information to set up an equation. This equation tells us that some currently unknown number of lithium atoms, which we are trying to solve for, have molar masses of 6.941 grams per mole for a combined mass of 34.705 grams per mole. To find this unknown number, we divide the total mass by the molar mass of a single lithium atom. Using my calculator, I found out that 34.705 divided by 6.941 equals 5. Therefore, the lithium molecule is made up of 5 lithium atoms. That's the end of this lesson, and if you have any questions, feel free to go back through the lesson again. Hopefully it'll make a little bit more sense if you review it, but I hope that everybody is beginning to understand this, and good luck.
Hi everyone, my name is Abigail and I'm from Massachusetts. Today I'll be talking a little bit about chemical equations. Chemical equations are used to represent chemical reactions through symbols. Each chemical equation has two parts, the reactants, generally on the left side, and the products, which are generally on the right side. An arrow pointing from left to right normally connects these two sides. Though chemical equations are useful on their own, indicating the physical state of matter of a given element or compound provides more information about the reaction. There are 4 physical states in a chemical equation: solid, denoted by a lowercase s, liquid, denoted by a lowercase l, gas, denoted by a lowercase g, and aqueous solution, denoted by lowercase aq. It is worthy to note that an aqueous solution is simply something dissolved in water. As we have established, chemical equations are very useful tools when used properly. However, some chemical equations have to be balanced, meaning that in its current state, it does not obey the law of conservation of mass. In simpler terms, an unbalanced chemical equation does not have an equal number of atoms of each element on both sides of the equation. For example, if there are 5 carbon atoms on the left side of the equation, there must also be 5 carbon atoms on the right side. Balancing chemical equations can be difficult, but it doesn't have to be. I suggest following these 3 simple rules. Number 1. Only change coefficients, not subscripts. Changing coefficients only alters the amount of atoms, but changing subscripts alters the ratio of atoms. Number 2. Balance one element at a time. In this example, you might choose to start with carbon. Once there are the same number of carbon atoms on each side of the equation, move to the next element. Sometimes, you might have to go back to an element that you previously balanced, as changing the coefficients often have a ripple effect. Number 3. I sort of mentioned this already, but keep checking the number of atoms for each element until the equation is fully balanced.
Hello, in this section of the lesson, we will be discussing the applications of balancing chemical equations in exercises that require us to find the amounts of reactants and products involved in a reaction. So, how can we use the concept of mole and the skill of balancing chemical equations to solve chemical problems in a lab setting or in practice exercises? Well, consider the following example problem. Automotive airbags inflate when a sample of sodium iodide is very rapidly decomposed. We are given the unbalanced equation that describes the process. Then the problem asks us to find the mass of sodium iodide needed to form a very specific mass of a product, nitrogen. Okay, so the questions we are being asked is, what mass of sodium iodide is required to produce 125 grams of nitrogen gas? So the first thing we should do in order to solve this problem is balance the equation. This way, we have the same number of atoms of each kind on both sides of the equation. Now we can begin working on the conversions we need to do in order to ultimately find the mass of sodium iodide required. But how? We will work backwards with the reaction, finding how many moles of nitrogen were produced. So if 1 mole of nitrogen weighs about 28 grams, then 125 grams of nitrogen equals approximately 4.464 moles. Now that we have the amount of nitrogen moles produced in the reaction, we can find the moles of acid using the proportions given by the balance equation. We know that for every 3 moles of nitrogen produced, 2 moles of acid should have reacted. Thus, we can estimate that 4.464 moles divided by 3 and then multiplied by 2 should give us the amount of acid we are looking for, about 2.976 moles. Now we only have to convert it to grams. We can calculate the molar mass of the acid as 22.99, which is sodium's molecular mass, plus 3 times 14, which is nitrogen's molar mass. Multiplying that by the amount of moles we just found, we get that 64.99 grams per mole times 2.976 moles is approximately 190 grams of acid, which is the value we were looking for initially. So now that we have already solved an exercise involving stoichiometry, we will introduce a new concept, limiting reactants. We will use the following analogy. We want to prepare cheese sandwiches, each of which requires 2 slices of bread and 1 slice of cheese. Upon checking, we find out that we only have 7 slices of cheese, but also only 10 slices of bread, which means we will only be able to prepare 5 sandwiches and 2 slices of cheese will be left over. The same idea can apply to chemical reactions, where one of our reactants is available in a proportionally greater amount than the other. Let's say we're given 100 grams of lithium and 50 grams of nitrogen. When we convert those to moles, using molar masses of each compound, we get that we have 14.4 moles of lithium, but only 3.57 moles of nitrogen. We know that for each nitrogen atom, we would need 2 lithium atoms to react, which means that for all 14.4 moles of lithium to react, there should be half that amount, about 7.2 moles, of nitrogen. However, all available nitrogen amounts to only 3.57 moles. The reaction cannot proceed after all nitrogen has reacted, so in this situation, nitrogen is considered the limiting reactant, the one that gets consumed first and thus limits the amount of product we can obtain. As a result, all 3.57 moles of nitrogen will react with twice that amount of lithium. 7.26 moles of lithium will be left over. In this context, lithium is the excess reactant, the one that will not react completely, as there is an extra amount in proportion relative to that of another reactant. In our sandwich analogy, the bread would be the limiting reactant, just like nitrogen, and the cheese that ends up not being totally consumed is comparable to the excess reactant in the example, lithium. We should always remember to balance chemical equations before attempting to determine what the limiting reactant is. If we don't do so, we risk our calculations being incorrect. Additionally, when we need to solve a stoichiometry problem, it is always a good idea to use the limiting reactants quantities as reference to calculate the amount of product that will be produced. Thank you so much.